Hello everyone, this is Yun from Meta Remote Present Networking team. Today, Bin and I will talk about how Meta scale audio and video experience for large group calls. Today, as the world is more and more connected, real-time communication technology has evolved as a vital tool to bring people together, both personally and professionally. In recent years, especially after pandemic happened, support large group call is increasingly important for remote work and virtual collaboration. In the past few years, Messenger focused on improving quality for small group calls and one-to-one calls. Large group calls present a unique set of problems. For example, we need to support many more participants, each of them with several video and audio streams. That means we need to handle much more audio and video packets. Moreover, we need to make sure the call is usable and accessible to all the participants, regardless of their network condition and devices. In this presentation, Bin and I will explore some key challenges along the way and how we resolve this problem by introducing new algorithm and design. So in the first session of this presentation, Bin will talk about audio challenges and how we scale audio technologies. For example, the dominant speaker detection and how we use dominant speaker to optimize our call experience, like audio capping. In the second session, I will continue to talk about video challenges and how we scale video technologies, like simulcast, temporal scalability, and a completely new design of bandwidth allocation. In the last session, Bin will talk about future works. Okay, now I will let Bin take over and talk about audio.
Thanks, Yun, for the opening. Hello, everyone. My name is Bin. I have been working in Meta for 3 years. Next, I'm going to talk about the audio scaling for large group calls. Compared with video, audio traffic is very small. Previous design only focused on small group calls with limited audio traffic reduction. For example, on the client side, we use DTX. If people are not talking, we are not forwarding. And we also have some more efficient codec, which help reduce the audio traffic. However, this is not enough for large group calls. Consider 100p or 200p. Especially consider the social nature of Messenger user, because not everybody are muted or silent. So if people are talking, there will be a lot of the DTX mode will be disabled and will cause a huge audio traffic spike. And also, even if everybody is muted, one receiver can still receive large amount of silent audio packets. We call it DTX packets. To solve this problem, we have introduced the server-side selective forwarding. So the high-level idea is pretty straightforward. Server-side will make a centralized decision and only forward top X most active speakers back to other participant. And we have two components to achieve this. The first one, dominant speaker, and the second one is audio capping. Before I jump into the detail of those two components, I want to talk about some critical factors that we need to consider. For example, server has very limited information to make a very high accurate decision because end-to-end encryption, and also the server-side decision must be as real-time as possible. The latency is very, very critical for us. And there are some other situations that we need to handle. For example, DTX, different frame size, stabilized audio forward decision, and PLC CNG. Next, let's consider about the dominant speaker detection. So if we look at from 100 feet, dominant speaker detection is a centralized component running on the server side with all the participant audio stream as input and the sorted speaker list ordered by speech activity as output. And the dominant speaker output will be sent to audio capping, where selective forwarding logic will be running to only send the top X most active speakers and drop the rest. Simple enough, right? Then let's look much more deeper to the dominant speaker. To make the dominant speaker working, there are few parties collaborate together. The first one is a client. When client encodes audio packets and send to SFU, the client has enough information to inspect the audio content and determine the volume of that stream. Then the volume information will be passed as an audio RTB header in each packet. And then once the SFU receives the audio packets, it gets the audio level for each participant and store it in a rolling window. We need to do this because speech is continuously. Any historical information is valuable to predict future speech activity. Next, we'll do the noise floor detection to avoid bias and to handle different noise situations. For example, we don't want to forward the people who joins from airport and drop the people who is joining from a home office just because the background noise level is higher for one person than the other. After we do the noise floor detection, we will detect how many active samples in different time window. So this is fair straightforward, right? So because we want to make the audio level from different people is comparable. The noise floor is used as a baseline, and the relative levels are computed to present how loud for each speakers compare with their background level. After that, we'll do the speech activity score calculation. So the high-level idea is that there are more active samples in each window, the most likely you are talking, right? So the speech activity score calculation will take how many active samples in each window and do a calculation and then generate one single number. So this number will be sent to different rankers. We need 2 rankers because we want to get different kind of fresh result. For example, dominant speaker, we need a very stable information. So we have a much more stable ranker. For sorted speaker needs, we need a much more sensitive sensor ranker. So if people start talking, we already detect that. So after that, the ranker will generate a top X most active speakers and send that information to the audio copy. So next slide shows, this graph shows how the audio capping and dominant speaker work together. So it's just a summary about what I have talked about before. The sender will send the audio packets with audio level to the dominant speaker, and dominant speaker did a centralized calculation and then send the sorted speaker list back to each media thread. And media thread will run the audio capping logic, and it will simply forward the top X streams and drop the rest. But keep in mind that SFU also need to track the forwarded or dropped sequence number range. So to make sure there is no sequence number gap after resume forwarding. So with this approach, we get very good result on the audio traffic reduction. For example, for a 20 people call, we achieve 38% reduction on the audio bill rate and a 63% reduction for the 50 people call. As a result, we see less congestion from server to receiver and also result in less packet loss and audio video quality improvements. That's pretty much all about the audio scaling. I'm going to hand over to Yun to talk about the video scaling.
Thank you, Bing, for the great talk on audio. In the next session, I will talk about video challenges and how we scale video technologies. In the first place, let's review some concepts and existing technologies together. MWS means multi-way server. It is a selective forwarding unit with a set of media features like bandwidth allocation and bandwidth estimation. Uplink means the traffic from client to the server, and downlink means the traffic from server to the client. BWA means bandwidth allocation. It is the core module in SFU playing decisive role in media experience. It decides the uplink video target bitrate and also the downlink bandwidth allocation. Existing bandwidth allocation algorithm works well for smaller group call and provide good quality. However, as the size of the call increases, it raises several problems. In the following slides, I will walk through 4 key challenges we come across along the way. The first challenge is lowest common denominator. A participant with bad network connection could become the bottleneck of this call and bring down the whole call experience. In the following diagram, client 2 has a limited bandwidth of 500 kbps. Each of other 10 participants could only upload 50 kbps video to accommodate the bad network of client 2. That means even though this participant has good network connection, they have to suffer from poor quality here. The next problem is video oscillation. In order to maximize the downlink network usage, bandwidth allocation module takes all participants' uplink and downlink network condition into consideration. That means any participant network change could oscillate the entire call. For example, in the diagram on the right, we can see excessive oscillation for both simulcast layer structure and their target bitrate throughout the whole call. The next problem is our design is not optimized for user experience, so each downlink is evenly distributed to all the participants. That means the pinned user will share similar quality as other thumbnail users. In the following example, client 2 has a downlink of 1 Mbps. 100 kbps budget will evenly distributed to all the participants. Client 1, as the pinned user who takes over the whole screen, will share similar quality as the other participant who is played out in a very small window. The last problem is we cannot handle super low bandwidth users. Each participant in our system requires a minimum bandwidth to receive all the subscribed streams, which could be a pretty large number in large group calls. In the following example, video requires a minimum bandwidth of 50 kbps. Even though client 2 has a limited bandwidth of 300 kbps, our system will still forward over 500 kbps traffic to this user. This user will experience serious congestion and the call will be not usable for this user with low bandwidth. In order to resolve these problems, we introduced several technologies that simulcast, temporal scalability, video pause, and a new design of bandwidth allocation algorithm. A foundation issue to this problem is a single stream cannot fit all the use cases and the network condition. Simulcast is a technology to provide multiple different video layers at different bitrate with different quality. In the following diagram, client 1 with the simulcast capability will provide 2 video streams at 50 kbps and 200 kbps. Client 2, as the bottleneck of this call, will subscribe base layer, while the other users with good network condition will subscribe high-quality layers. Temporal scalability is a technology to encode a video sequence at a set of different layers. That means the video stream with temporal scalability could be decoded at a different frame rate accordingly. Simulcast could work together with temporal scalability to provide multiple different video layers at a different bitrate with different resolution and different frame rate. In the following example, our system could provide 3 special layers at a different resolution, each of them with 2 temporal layers. In total, our system could provide 6 different video layers to accommodate different use cases and different network conditions. Video pause is the very last strategy to address the low bandwidth users. So it will reduce subscription for important video streams. In the following example, video still require a minimum bitrate of 50 kbps. Client 2 with a limited bandwidth of 300 kbps will now only subscribe 6 participants instead of 10 to accommodate the limited downlink. In order to make sure all these technologies working together, we replace the existing bandwidth allocation algorithm with two completely new modules: per endpoint bandwidth allocation, which decides uplink, and stream subscription manager, which makes downlink decision. Per endpoint BWA decides the video layers and their target bitrate for each uplink independently. It allocates constant bitrate ladder, which is well designed for different use cases like pinned view, grid view, and thumbnail view, and also different network conditions, just as the diagram on the right. This design stabilizes the user experience and resolves the lowest common denominator problem. Stream Subscription Manager is an intelligent stream subscripting logic for each participant. It will decide the downlink subscription according to available uplink video streams, downlink network condition, and user viewport size. So it is purely a priority-based model. We will always try to reserve enough bandwidth for audio usage in the first place, and then we will try to subscribe high-quality layer for important video streams like dummy speaker and pinned user. Finally, the left bandwidth is allocated to unimportant streams. If the bandwidth is not enough for all the subscription, video pause will kick in and drop video streams accordingly. Our design focuses on the stability of downlink subscription and try to avoid simple maximizing the downlink bandwidth usage. In the next slide, this diagram shows how Stream Subscription Manager and per endpoint BWA working together for large group calls. In the last, I will go through an example with all these technologies. So Client 1 and Client 7 providing 3 constant video layers at different bitrate. And let's assume all the other participants subscribe Client 1 to Client 7 in this call. So participant 0 has a limited bandwidth of only 150 kbps. At this time, Stream Subscription Manager will decide it doesn't have enough bandwidth for all the subscription. It will drop 4 video streams while subscribe like base special layer and base temporal layer for the other 3 important video streams for this client. For all other participants with normal network condition, depending on the view mode, Subscription Manager will make the decision accordingly. For pinned mode, Stream Subscription Manager will forward high-quality layer for pinned user and base layer for other thumbnail users. And for grid view, Stream Subscription Manager will always forward a middle layer for all these participants. After launching all these technologies, we see very promising results from both video quality and video oscillation. Okay, in the next, I will let Bin take over to talk about future works and the next steps.
Thanks, Yun, for the great presentation. That's pretty much what we did for audio and video scaling. Going forward, we never stop our investment on many interesting features. Like for audio, we have dynamic audio capping, which we are only for the active speakers. And for video, we also have dynamic video layer structure for different viewpoint. And we also have more intelligent stream subscription manager. So stay tuned. Thank you.